It's just after sunset in January over Texas. A Learjet 35 is trying to land at San Marcos, Texas, after a storm has just passed through. They're high and they're fast. The captain is struggling to get the autopilot to track the ILS localizer. Approach control asks if they'll be able to make their descent. Even though they get the airplane onto the glide slope by the final approach fix, they'll cross the runway threshold at 250 feet or 5 times the normal height and over 20 knots faster than their planned approach speed. San Marcos Tower controllers watch the airplane overfly the first half of the runway and even say, "Not much runway left," over the radio. The airplane comes to a stop 300 feet past the end of the runway, having lost its nose landing gear. Over Florida, a Cessna 172 is in the practice area. Aboard, a trainee and instructor are practicing several simulated emergency scenarios. This includes emergency descents. Equipped with a more modern instrument panel, the airplane provides the pilots with more alerts and enunciations than older Cessna 172s. The instructor notices an alert about high oil temperature. Having experienced a crankcase failure before, he's fearful something similar may be occurring now. He immediately takes control of the airplane and tries to land at a nearby airfield. They're high and fast, though. The instructor deploys full flaps and does a forward slip. Despite this, they touch down more than halfway down the runway. The airplane hits a ditch and winds up upside down in the brush. Nobody is seriously injured. At Johnson Creek, Idaho, a Cessna 206 winds up high and fast. The pilot lands long, and he struggles to get the airplane onto the runway. At the last minute, he executes a go-around, narrowly missing terrain. Some months later, observers witness the same thing happen again. This time, the plane impacts terrain with no survivors. These few crashes all share a similar, undesired aircraft state. Too much energy that the pilots could not dissipate. Let's explore this in theory, in flight, and within ourselves. My name's John. I have some planes. Let's try some stuff. Dissipating energy, getting lower and slower, often is part of a cascade that overwhelms pilots and flight crews. Around the time we have to think about getting down is about when we discover there's been some change to the weather or we're assigned some new routing or restriction. It's pretty easy to wind up a little bit high and a little bit fast as we handle some other task. We have to work even harder. So getting energy off of the plane is really about giving us more ways to manage our workload. The busier, the more task saturated we become, the harder it is for us to access the strategies and tactics that can best handle a situation. When we talk about why an airplane winds up with too much energy, why a pilot might struggle to dissipate that energy, or even when we talk about ways we can get rid of energy that we want to lose, what we're really talking about is the pilot or the crew's mind. What we do in maneuvers, with the airplane, the automation, how we manage a flight, those are all offshoots of the pilot or the crew's mental state. Here's the pilot. The pilot has to be aware of some condition, then make a decision about it, and execute that decision. Let's say the pilot figures out that he's some combination of high and fast. To become aware of that condition, the pilot has to sense it. With his eyes, he can see instruments, outside references for airplane control, and hazards outside. With his ears, he can interpret noise, gain data from the radio, and collect data from the crew by intercom. The same goes for all the other senses. Once this information is taken in, the pilot's mind has to understand it, prioritize various factors, and come to a decision. This involves a very long list of things when you think about it. Training, the pilot's knowledge, physiological factors, psychological factors, and external pressures. The list goes on and on. With the decision made, the next thing we do is execute that decision. That could be modifying our automation, adjusting our configuration, or doing pilot stuff. I would like to offer an idea for your consideration. The airplane can only be put into what we will call a bad energy state if there's some kind of problem in the crew's decision loop. If a pilot is ahead of and engaged with the flight, he has some idea of how to get from here to there with recovery and escape plans. To wind up in what we'll call a bad energy state, a change has not been anticipated and a recovery or escape plan either has not been conceived or has not been triggered. It's crucial to note that this does not mean the pilots or crews are bad. It means some combination of factors has already exceeded the pilot or the crew's brain power. All brains have limits. Even the best of us are vulnerable. But if we accept that a bad energy state is a symptom of task saturation, we can now understand why that same pilot or crew might not have the decision-making capacity in that moment to initiate a go-around, successfully dissipate energy, or execute a particular maneuver while maintaining adequate aircraft control. Let's get back to that Learjet in San Marcos, Texas. The captain is a smart guy, and aviation was not his first career. He graduated from Carnegie Mellon University in 1974 with an electrical engineering degree. Subsequently, he worked as an electrical and software engineer. He holds 2 U.S. patents relating to controllers and simulation memory, and he then held executive positions on the board of directors for a credit union. Outside of recreational flying or flying skydivers, he came to professional aviation relatively late in life. Starting in the mid-2000s, he flew freight in twin Cessnas, served as a first officer for a regional airline, and then became a pilot for this air ambulance operator involved in this accident. Working at the air ambulance company, he rapidly held management and training positions. He became chief pilot starting only about a year before the accident. He was 71 years old at the time of the mishap and reported having around 11,000 hours total time and about 1,700 in the Learjet. The first officer in the right seat was only 27 years old. He had just under 800 hours of total time and 165 hours in the Learjet. As a relatively new pilot, he is sitting directly next to his recently promoted chief pilot and company instructor. The cockpit of the accident airplane looked something like this. This is a sister plane from the same company. The cockpit is very similar to the ones I used to fly in some previous positions, but it's very different to this cockpit, a Canadair regional jet, which the captain was flying previously. We can see that this is an early 80s vintage jet. The panel is thoroughly adequate, but it has some limitations. Because the airplane was built in 1981, the auto-flight systems on the plane were capable of flying a localizer or VOR course. That's how it came from the factory. And what that means is that if the plane's auto-flight systems could fly an RNAV approach, some reconfiguration of the plane's avionics would be required. And the way these avionics would have to be configured would be specific to this plane. The type-specific training for the crew was conducted at a Part 142 simulator facility. That's like flight safety, Symptom, Simuflight, etc. This is great training, but the simulators have to be representative of the Lear 35 type as a whole. The simulators don't need to have exactly the same aftermarket avionics installations. The captain completed his annual recurrent training and instrument proficiency checks in the simulator about a year before the accident. His line check, a check to ensure he's flying within company standards, was also completed about a year before the mishap. And that line check is typically done in the airplane. It's just a check to make sure the pilots aren't deviating from company procedures. The other thing we can see here is a large placard stating that the thrust reversers have been deactivated. Airplane performance is not calculated on the availability of thrust reversers, but a system to help stop the plane and remove residual thrust on landing is not available. The day of the accident, there were 5 people aboard the jet. The typical crew of 2 pilots and 2 flight nurses or flight paramedics was aboard. The 5th person was an OBGYN from Albuquerque. This means that this was a live flight to do some kind of medical procedure that necessitates the flight of a jet. At 4 o'clock, about an hour before landing, the crew received a METAR at San Marcos reporting light northeasterly winds and 1,300-foot ceilings. Weather was in the area, however. As they got closer, the crew heard a plane execute a missed approach at Horseshoe Bay. That's over here, not far from San Marcos. The Horseshoe Bay Airport has 2 private approaches that get planes down to about 600 feet above ground level, and that's lower than the weather that was being reported by San Marcos. If the weather at Horseshoe Bay was similar to the weather at San Marcos, airplanes should be having no problem at all landing at Horseshoe Bay. We like to think of cloud ceilings as flat, level bases, but often, especially around more active weather, the cloud bases aren't flat at all. It's not uncommon to have an airport reporting weather that's acceptable for an approach, but have lower cloud bases away from the field exactly where you need to be in clear air to visually acquire the runway environment and land. At 5 o'clock, less than 11 minutes before the crash, the captain directed the first officer to listen for weather updates at San Marcos. San Marcos was still reporting winds 060 at 8, 1,300-foot ceilings, and 10-mile visibility. So when the crew was offered the RNAV approach to runway 8 or the RNAV approach to runway 35 at San Marcos, the captain asked about the plane that went missed at Horseshoe Bay. This particular Lear 35 was not able to provide vertical guidance to the airplane's instruments for RNAV approaches. And what that means is the approaches offered could only get the airplane into a position similar to the one experienced by that other plane at Horseshoe Bay, and that other plane wasn't able to land. So the captain decided to take an approach that provided vertical guidance, and that meant the ILS to runway 13. If ceilings and visibilities deteriorate below what was currently reported, this approach would give him the best chance of a successful landing. About now, some interesting things happen in the crew dynamic. With the airplane situated about 27 miles northwest of San Marcos, setting up for the ILS to runway 13 means the crew has less time and less distance to lose altitude in order to make a critical condition at a position called Gary's, which is the final approach fix for this approach. If the plane is too high or too fast at this fix, a successful landing is doubtful. The airplane is high and it is fast. Air traffic control even asks them about the descent, but it's not in a bad energy state. The captain will get the airplane down and on speed and configured by Gary's. In the crew's mind, there is a way to get from here to there, and the crew is aware of it. But while the crew can figure out their energy management by Gary's, during this period we start to see the first indications of the crew's decision loop starting to break down in the cockpit. The crew is trying to get the airplane's autoflight systems to track the ILS near the limits of where the plane can receive usable signals from the ILS. This is not abnormal or improper, but it does occupy their attention. About the same time, the airplane enters an area of precipitation and the first officer turns on ice and rain protection for the airplane. As the plane rejoins the ILS, the captain is becoming more confident in autoflight systems. The first officer, however, is becoming less confident in those same systems. The first officer states, "I wouldn't trust the autopilot." The captain does not respond. He calls for a flap configuration. "I wouldn't trust the autopilot" is an advisory statement. It's not a clear declaration like, "Autopilot has failed," or a directive like, "Go around." So it's possible the captain was silent because the plane's systems did start tracking the ILS properly, and the captain thought that the first officer's issue was resolved. It's also possible the captain missed the first officer's advisory about the autopilot entirely. Regardless, one or both of the pilots had an open concern that was not resolved as the airplane crossed the final approach fix. And this is what was knowable to the crew in the cockpit at the time. So let's talk about what the crew could not know about. To do so, we'll watch these guys demonstrating a takeoff in a 737 simulator.
V1. Rotate. That's great.
Gear up.
Gear up. LNAV. LNAV. Gears up. Throttle on. Safe clamp closed. N1. Clamp.
Hear how the pilots are talking to each other through the takeoff? At a lot of airlines, charter operations, and defense operations, there are standardized calls that are made during critical phases of flight, and we expect to hear things like localizer alive, localizer captured, etc. These standardized calls aren't memory exercises. They serve real and proven functions. They force us to pay attention to unplanned deviations in pitch, roll, or speed. According to one of their pilots, at the time of the accident, the operator did not have formalized callouts or other SOPs. And this is understandable for a small operation where all the pilots get trained at the same simulator facility. On slope and course at Gary's, the crew had no way of knowing that their awareness of potential deviations was degrading. There was no SOP trigger to call them back to flight path awareness from potential distractions. Another, more important detail was not knowable to the crew at the time. When the captain selected runway 13 for landing, he mentioned that the winds were light with an 8-knot crosswind from the left. Flying the ILS approach to runway 13 in these conditions would have had the crew stop about this far down the runway, provided they did everything properly. This leaves a lot of margin for error. When the crew checked the weather just 10 minutes before landing, the recorded weather confirmed that they were still dealing with that same light crosswind. In fact, the weather had changed, and the recorded weather report, the ATIS, had not been updated by San Marcos Tower. The crew was actually going to be landing with a nearly direct tailwind of 12 knots, gusting to 24 knots. This is actually outside of the Lear 35's limits. The NTSB did a performance analysis and found that, if everything was done properly, crossing the end of the runway at 50 feet, etc., the jet could be brought to a stop about here. The margins for error are now much smaller. And this calculation was done with a 10-knot tailwind, the limit of the charts published for the Lear 35. The NTSB performance analysis actually calculated that the airplane was experiencing about 15 knots of tailwind at the time of touchdown. A linear extrapolation of those charts to a 15-knot tailwind has the airplane stopping about here. Without access to up-to-date information, the crew thought they could stop the plane in just a little over half of the runway length. In reality, they had no margin for error at all. It's possible that they could have noticed a higher than normal ground speed or sink rate, but it's not uncommon to have a tailwind at the final approach fix that veers or backs into a crosswind at the runway. So I will go ahead and say that there was not a practical way for the crew to know that the ATIS at San Marcos was dangerously inaccurate. So let's place ourselves back into the cockpit of the plane as it crosses the final approach fix at Gary's. The crew did get a little bit high, but they knew why. They were going to set up for the ILS runway 13, and they managed to get down without trouble. As they crossed Gary's, the pilot monitoring, the FO, and the pilot flying, the captain, have different degrees of confidence in the flight, and this issue is either undetected or unresolved. The FO and captain have no procedures that establish expectations about the pilot monitoring's role in maintaining flight path awareness. So they have no easy way of detecting a degradation in flight path awareness of the pilot monitoring. And they think that they have plenty of landing performance to spare. In fact, the weather has changed and they're landing with an excessive tailwind, and they have no easy way of detecting this. On an ILS approach, the pilot flying's attention is entirely on his flight instruments. In this example, a Boeing-style PFD display. The closer the airplane gets to the ground, the more precise the signals become, and the more precise the flight path needs to be. The first officer starts calling out visual references that he can see out the window. This is not wrong, but it can be unhelpful. When the approach lights and PAPIs, lights that provide vertical guidance, are visible to the first officer, he says, "All right, there we go. Landing is assured. Ahead 12 o'clock. Do you see the PAPIs on the left?" This is still 200 feet above minimums, before clear visual references are needed or expected. Still, the captain flying the airplane is called up and away from his flight instruments to look outside for these references, and he does so. Earlier than necessary, his attention is diverted away from his flight path and outside of the plane, looking for dots of light in cloud through a rainy windshield. As he searches outside, he lets the airplane level off 200 feet above minimums. By saying landing assured, the impetus for a go-around has been subtly hindered in the crew's minds, and the impetus to land has been increased. Critical analysis is failing. The pilot monitoring does not alert the pilot flying that they are drifting above glide slope. They are becoming high, starting to carry too much energy, and the crew is not aware of it, at least not adequately. And this is where stabilized approach criteria get defeated. If nobody is monitoring the approach, nobody is going to detect when the approach becomes unstable. With both pilots' attention channelized on approach lights, nobody notices things going wrong. Instead, the first officer says, "Right there, straight down, look down." The FO knows they're in an unacceptably high energy state. They're looking straight down, as he says, at the pappies. Still, he's coaching the captain to land rather than calling for a missed approach. The crew is now unaware of their flight path. They have committed to landing. The pappy lights, showing them that they are high on the approach, aren't registering with either pilot. The captain pulls the thrust levers to idle. The airplane descends at 2,000 feet per minute towards the runway. No JIPWIS calls are heard, and the pilot monitoring never mentions the sink rate. This is where the physics lessons, the weirdo flying, the human factors, and all these accidents come together. There are only a few situations where a pilot needs to act before he thinks. For a civilian pilot, those would be things like maintaining or regaining control of the airplane, especially below pattern altitude. Terrain escapes and wind shear escapes might be a couple other examples. For a big effort in flight to work out, a pilot needs to know and be able to use some critical information. That's basically three things. He needs to know the condition of the flight. He needs to have a way to get the flight from its current state to its desired state. And crucially, the pilot has to know if this information is missing or if it's inaccurate. As the captain is descending at 2,000 feet per minute to the runway, he doesn't know the condition of the flight. He's not aware of glide slope deviations, and even seeing the white pappies, that information isn't usable to him. He doesn't know about that tailwind. He thinks he's got a way to get the airplane from its current state to the desired state, touching down on the runway, but that is based on inaccurate and missing information. If we go back to that Cessna that wound up high and fast in Florida, we can see something similar. The instructor was missing critical information. He thought his engine, which was perfectly good, was failing. Convinced that he needed to land immediately, he wanted to get the airplane on the ground as soon as possible, but he didn't conceive of a way to get there. To his credit, he even says so in his statement to the NTSB. He could have used S-turns and other maneuvers. That crash at Johnson Creek did not have any survivors that could tell us their story, so we have to work with what we've got. Johnson Creek, Idaho has some special considerations, so much so, in fact, that the Idaho Department of Transportation made this video, also using a Cessna 206, to detail how to get in and out of Johnson Creek. They specifically mention that the plane has to be placed close to terrain.
But the ridges among the east and the west prevent pilots from flying a regular traffic pattern. Approaching Johnson Creek, pilots will see that the traffic pattern altitude is well below the ridge lines to either side of the runway. This will force you into flying a closer than normal upwind or downwind position around the airport, again hugging the right side. This will put you close to the mountains and the trees while flying to upwind.
They specifically mentioned that a late go-around places the plane in a position where it may not be able to outclimb terrain.
Energy management is crucial, and if you arrive at half-mile final and you're too fast or too high, it's time to make an early decision for go-around. A late decision to go around may leave you unable to outclimb the trees and terrain. In this case, your best chance is toward the lower trees to the left of the Brian Howe.
But the accident pilot and plane repeatedly wound up landing long and making late decisions to go around. So it's safe to say that either he was missing critical information, or he failed to understand or appreciate it. Since he was consistently landing long at Johnson Creek, it's also safe to say that he did not consistently have a good way to get the airplane there. Repeatedly, he struggled to get the energy that he had accrued off of the airplane in a way that allowed for a successful landing. Previous successful late go-arounds may have skewed his perceptions of hazards as well. He may have overestimated the risks of being close to terrain or maneuvering while underestimating the hazards of a late go-around, especially when afternoon temperatures started to creep up. Does this crash at Johnson Creek, another one where the pilot was struggling to get energy off of the plane, fit into the same model of missing information and no way to get there? We know the pilot had been flying for about 5 hours the day of the accident, and they were arriving later in the day than most would like. There's a note in the guide to the Johnson Creek Airport that mentions afternoon winds, katabatic winds, that developed there. Fatigue may have been a factor. It's also possible that fixation, get-there-itis, was factoring as well. Witnesses the day of the accident observed the airplane higher than normal as it was in the pattern. So it's also possible the pilots simply were not comfortable putting the airplane where it needed to be, which is pretty close to mountains and trees. What we do know from witness statements and video of previous arrivals is the pilot crossed the normal abort point with too much energy, and he failed to recognize or appreciate this condition. So critical information was missed, but we don't know why, and we don't know exactly what. We also know that at some point the pilot did know he needed to get the plane down, but he struggled to do so. This is evidenced by long landings and improper bounce recoveries. So he didn't have a way to get the airplane from where it was to where he wanted it in the condition he wanted it to be in. There's a pattern with these accidents that I believe I'm starting to illustrate. What can we do about this? To make it easier to tackle these things, let's rename all of this stuff about the flight's condition and missing or bad information into something easier to say. Recognition of the problem. And let's turn all of my cutesy wording about finding a way to get there into something more useful. Execution of a solution. Let's start with the execution of a solution piece first. Let's imagine we're flying along and we just point the airplane's nose towards the ground. Sure, we'll descend, but we'll also pick up speed. Once we're low and fast, we can scoot along for miles, waiting for this speed to slowly decay, or we can pull the nose back up and turn that speed back into altitude. So getting the airplane up or down isn't a simple point-and-shoot affair. Transitioning between high and slow and low and fast is basically what we're doing when we fly egg-shaped granny loops. When we're high, we're slow. When we're low, we're fast. The engine is putting about as much work into the airplane as drag is pulling work out of the airplane. So let's take a little look to see how force, work, and power all do different things to affect the energy state of the airplane. If we go back to looking at our loopy cartoon plane, we're keeping about the same amount of energy on the plane. We're just altering the ratio of kinetic to potential energy. The engine is working about as much energy into the plane as drag is working energy out of the plane. So if we want to get down, the plane needs to lose energy. If we want to get up and fast, the plane needs to gain energy. That's thrust, power, and drag stuff. If we keep the plane at a constant speed and angle of attack when we add thrust, after maneuvering settles down and the airplane returns to equilibrium, the angle of climb is determined by thrust minus drag plus the aft component of weight. Here's a formula from aerodynamics for naval aviators if it helps. The critical factor is the difference between thrust and drag on the plane. If there's no thrust on the plane, things simplify. Angle of descent is controlled by the amount of drag versus the forward component of weight. In equilibrium, lift is essentially equal to weight. This is why we get our best angle of glide at conditions that provide the best ratio of lift to drag. Whether you're descending for angle or rate, if you want to get down, you're going to need minimum thrust or power and maximum drag. So we need to stop making power and thrust. So here's a fake European 1960s jet. Our friend here is higher and faster than he'd like, so he pulls the thrust to idle. Jets are generally pretty clean. This means they're pretty scooty even when the thrust is pulled to idle. So engineers build in a number of drag options. There are speed brakes. Often speed brakes are just a function of wing spoilers, but sometimes they're panels mounted elsewhere on the plane like the rear fuselage. They work best at high speeds. There are flaps which work best at low speed, and of course we can use the landing gear as a drag device too. Most of the people watching these videos are probably flying planes with propellers and fixed landing gear. Engineers assume props make plenty of drag, and they're right. Pulling the power abruptly to idle is not always a smart thing to do, however. We can also fly the airplane in ways that create more drag. We can dive to inefficient speeds, and we can also load up the wing to create lots of induced drag. Here's a T-38 HUD as the pilot does an overhead brake. The speed tape is on the left side of the HUD, and I've sped this up. Pay attention to how fast the speed decays in the turn versus how fast it decays after the plane rolls to level, and before the gear is deployed. So that's enough theory for one video. Let's see what these things do in the actual airplane. Around best glide speed, or 60 miles per hour in my Piper Cub, we lose about 600 feet per minute every time we try it. And over a number of runs, it looks like we cover about 1 nautical mile at the cost of about 700 feet or so. In most airplanes, minimum sink speed is usually only about 15% or so higher than stall speed. So in the Cub, that translates to about 45 or 50 miles per hour. At idle power, with my engine and prop, we see a sink rate of about 400 feet per minute, and we lose closer to 900 feet per nautical mile. There's a lot of instrumentation error in the Cub at these low speeds, however. Idle power and 100 miles per hour straight ahead, we sink at about 2,200 feet per minute. Idle power, 100 miles per hour, but with 60 degrees of bank, we lose about 2,900 feet per minute. This time with a full slip, 3,800 feet per minute. In an engine failure scenario, best glide is pretty useful, and most of us know this. As battery-powered devices proliferate, cockpit and cabin fires become a more considerable hazard. So some of the more rapid descent options may also be worth considering as well. But these are all scenarios which are crystal clear to the pilot. What works when things aren't so clear? One of those scenarios would be when you're high, but for some reason you're not going around to make another attempt at the landing. So I collected a bunch of footage of myself putting the plane in a higher than normal energy state and figuring out ways to get it down. Let's pretend we're gliding our yellow biplane into inflatable advertising cone thingies. Watch the vertical bearing changes to the top of the cones. The red cone we're going to overfly. It's close and you see it move down the windshield and pass beneath us. Judging whether we'll hit the top of the red cone is easy because the change in vertical bearing is pretty big. It's pretty easy to pick up on. Judging whether we'll hit the top of the yellow or the top of the blue cone is tougher though. The differences in angles are smaller. You don't get a clear idea of what we're going to hit and what we're going to miss until we get a lot closer. And what this means is fine judgment of our glide path by eye takes a lot of practice and it takes a lot of attention. We have to work our minds extra hard because we're trying to get what we need to know from data that has relatively low resolution. This is also why it's easy to lose track of your airspeed, reserve lift, or AOA when you're trying to play things out just right. It's natural to focus on your vertical bearing to judge your glide path. So here we are in the Cessna 170 with a simulated engine failure and a clear traffic pattern. At this distance, it's hard to tell whether we can make the runway. So prudence has me keeping my speed at best glide until we know for sure that we have the field made. To land precisely, I need to be about 10 to 15 miles per hour slower than my best glide speed. Now I've gone from low on energy to having too much of it, and this becomes a full flap landing, touching down about 50 feet past the numbers. So even in a low energy situation, you're still going to need to know how to get rid of your energy fast in order to be anywhere near precise. But you already know how to fly. The bigger lesson is one in human factors. Whether we're talking about carrying power into a spot landing, an engine failure scenario, or landing out of a circling approach at night without vertical guidance to a runway, we have a judgment call to make about our energy management, and that judgment call is only as accurate as the information we have in front of us. Reserve lift indicators, AOA indicators, are often placed on top of instrument panels or even integrated into a HUD, specifically so we don't have to take a second or two to look at an indicator. This is because we're spending that much energy trying to discern fine energy management details from rough external cues. Trying to get fine details into the cockpit requires a pilot who's able to receive and process those details. Whether you're relying on an AOA indicator or tactile cueing from the airplane, the data we're using is only as good as our fatigue level, proficiency, our sensors, instrument calibration, display lag, etc. Imagining that we're going to reliably thread a needle from several miles out, especially in the real world and real operational conditions, that's just not realistic. So let's look at some energy dissipation options, starting with a typical forward slip from our pre-solo training. So here we are a little bit high in the Cub. We have forward slips available to us. Slips make the plane more draggy and the wing less wingy. The great thing about a slip is it offers very fine control of the plane's drag, and you can use anywhere from no slip at all to a full slip, and there's very little time delay involved. As soon as you yaw your nose away from the relative wind, out of coordination, the energy is coming off the airplane, and as soon as you yaw the nose back into the relative wind, into coordination, you're back to a normally performing craft. My younger daughter wants to say hello to everybody. Let's take a look at a variation on the forward slip. This time we're closer to normal in terms of our glide path, but we're fast. Our airspeed indicator, along with the airplane's feel, its tactile cueing, tells us that we're fast. We can still use a slip to get rid of energy, only this time we're dissipating kinetic energy instead of potential energy. So we can use a slip to go from being fast to on speed. I'm not making any brilliant points here. Make plane draggy, plane gets draggy, right? But you already know how to fly. The point with both of these slips is the pilot has to be able to know whether the plane has too much energy or not. The pilot's mind has to have enough free capacity to explicitly or implicitly observe, evaluate, and act on the information available. If for whatever reason we cannot make the airplane more draggy, we can also give ourselves more distance and more time to dissipate energy, and this can be done with S-turns on final. Occasionally you'll see airplanes that we fly for work doing this. Usually this is requested by air traffic control for spacing rather than energy dissipation, but we still do it. Here's a picture of Air Canada doing some gentle S-turns at Las Vegas. If you imagine a runway, there's a cone of positions and energy states from which an airplane can land. And depending on your judgment, there's a tighter cone which you'll find acceptable to land from. So this cone essentially moves off the approach end of the runway some distance, and that distance is set by the pilot's judgment, among other factors. Typically, the plane is turned on to final some distance out, and energy is played out on the final. If a plane is low on energy, however, say low, slow, far away, whatever, you may see a pilot turn directly towards the runway or directly to a point where he can line up on the runway. There's less distance to cover and less time to burn. That clip I just used of thinking I was low in the 170, I'm doing that in that clip. So if cutting the distance is good for a low energy state, giving yourself more distance to cover and more time to burn is good for a high energy state. Sometimes this can be deliberately overshooting the final. Sometimes it can be a series of turns along the final. Here's what overshooting the final and turning for the numbers looks like in my plane. I was experimenting with new camera mounts and settings here, so the camera is at a weird angle that makes it hard to tell the amount of bank being used. We're only using maybe 30 degrees of bank here or less. Anyway, there's the runway. We're going to overshoot the final a little and reevaluate our condition when we turn back towards the field. We might have lost just a little too much energy, so we aim straight for the numbers. At unfamiliar airports, offset finals with a high workload are a great way to set yourself up for a wire strike. And that increased workload is the real risk here. So let's try demonstrating the same thing, but this time let's build in a little bit more margin for foul-ups. Now we're managing both energy and risk, and we're doing so in a couple of ways. We're crossing the end of the field straight enough to keep us alert for hazards close to the ground, and high enough that we aren't going to snag a wire that we might not have noticed. We can maneuver the plane for rough energy management. For fine energy management, we have flaps, and if terrain and conditions permit a lower angle of approach, power would provide very fine energy control. Today, I'm keeping it a little bit steep. There's the runway all the way down there. Like before, we cross the final, but this time we don't try to get it just right. We only try to get the airplane into the ballpark of good for our energy state. Now we turn back to intercept the final at some distance from the runway. By getting the plane into the ballpark of good rather than just right, we have enough spare brain power to play our remaining drag or our remaining power as necessary to make a good enough landing. And that spare brain power is really necessary close to the ground because close to the ground is where we're liable to get surprised, and close to the ground is where those surprises can become very costly indeed. If you remember your middle school trig, our progress towards the runway is our ground speed times the cosine of our track deviation. Or simply put, it means we have to turn a lot to make this maneuver worthwhile, otherwise we make the plane all wiggly for nothing. And if it looks like I'm getting kind of busy, it's because I'm getting kind of busy. And if you need to do this type of thing to make the runway, is there really a good reason not to just go around and try again? That takes us from execution of solutions to recognition of when we're up a creek. To help understand difficulties around getting pilots to recognize issues before they bite, let's take a look at some safety data. Year over year, we used to see some pretty significant improvements in accident rates and fatal accident rates per flight hour. Back then, we were able to deal with the easier stuff to work on when it comes to flight safety. So, for example, after 1965, it took us about 20 years to cut the hourly fatal accident rate about in half. Reliably, that happened by about 1985. It's taken us 40 years, barring occasional good and bad years, to consistently cut that accident rate in half again. Our progress is much slower now. We're working on more pernicious issues, and those go beyond simple technical considerations. To drive this point home, think about the tools and cockpits available to a general aviation pilot in 1965 and in 1985. A pilot from either decade would be more or less at home in either cockpit. That 1965 pilot would have walked into a flight service station or made a telephone call to get a briefing, just as the 1985 pilot would have. In fact, the 1965 and 1985 pilots would likely be flying the same planes with the same instruments, the same engines, etc. With that amount of technical change, accident rates were halved in 20 years. Between 1985 and now, we've rolled out GPS with moving maps. We've installed synthetic vision on airplanes with terrain information. We've rolled out low-cost ADS-in options so pilots can check NOTAMs, view traffic, and get weather information en route. Every single manual, reference, approach plate is available to us at our fingertips. A lot of our airplanes even have parachutes on rockets to save us if things really go pear-shaped. A pilot who learned to fly in 1985 would not recognize the tools available to a Cessna or Diamond pilot today. Still, it's taken us twice as long to make similar safety progress. Pardon my eyes starting left and right. My script's on one side and my camera's on another. If we're trying to make it so pilots recognize when they're carrying too much energy, I think the data shows that equipment does help, but it's not a magic solution. And the same goes for checklists. Checklists help, but they're not magic solutions. So instead, I would like to focus on our ability to put ourselves into these pilots' shoes. And that requires us to truly know ourselves. All of the information that we take in and all of the processing that we do takes place in our minds. So we have to know how we feel when things are going well, but we also have to know how we feel when things are not going well or when things are going quite poorly indeed. So how do we feel when we're becoming task saturated? How do we feel after we've become overwhelmed? How do we feel when we're fixated or when we're experiencing target fixation? And this is vital because we can't deploy our various strategies to regain the initiative of a flight, things like doing a go-around, selecting a different runway, even applying a different technique, if we're not in touch with and engaged with the flight. And we can't be in touch with and engaged with the flight if we're not in touch with and engaged with our minds. So when we try to answer these unanswerable questions, why didn't they go around? Why didn't they S-turn? Why did they continue onto that runway? We may be better served by asking, how would I feel at this point? How could I be negotiated into going on? If things looked great 10 minutes ago, how would I know that I was in too deep? Those are the questions that would be helpful. For example, if I put myself back into that Learjet captain's shoes, I ask myself, would I have caught that unreported 12 to 25 knot tailwind? We discussed that a little bit earlier. I don't think I'd have caught that unreported tailwind until around minimums when an expected wind shift didn't happen, and that's if I'd have picked up on it at all. The first officer thought that the captain was a fool, and the captain most likely picked up on this. We all sometimes fly with people who think that they know better than us. Sometimes they do, and sometimes they don't. When this happens, there are a lot of ways our reactions can be inappropriate. Either we become defensive or we become sheepish. We need to know how we feel when we're having either reaction so we can address the related hazards. And those same factors apply to the first officer. We've all flown with people that make us think, holy cow, how did you make it into this cockpit with me? When we have these thoughts, we often follow them by focusing excessively on the other guy's minor mistakes and ignoring some of our own glaring errors. Could I see myself being like this first officer? Yeah, I have been like that first officer. We see echoes of this in the statements provided to the NTSB by the first officer. Aside from mentioning a need to be more forceful in his statements, he makes little mention of his own flaws. He does go out of his way to say that the captain froze and he should have never been in command of that jet. His disdain for the captain was perhaps even deepened after the event. Another aspect of knowing ourselves is understanding our fears and our biases. The instructor in that Cessna in Florida mentioned that he could have S-turned to dissipate energy in his statement to the NTSB. We also know that the engine was running fine when he decided that there was an impending emergency that required an immediate landing, and this was due to a previous experience with an engine that was coming apart. Fear, which is different from startle and surprise, channeled appropriately, can be a healthy thing. Managed, fear can cause us to focus, arrange our thoughts, and get serious about a challenge. Unmanaged fear does the opposite. When we experience fear, our amygdala tries to take control of our brain, and it focuses our senses very intensely on the thing that we're afraid of. So we notice all the pointy teeth on a tiger that might be trying to bite us, but this comes at a cost, and that cost is other brain functions. Moreover, we have fear memory. So if we are afraid of something once, we become more sensitive to it. Now when we hear a rustling in the grass behind us, we want to jump out of the way of a tiger, whether that tiger is there or not. So our amygdala prioritizes fast action over judgment. Sometimes this is a good thing, sometimes it's a bad thing. So for us to get the benefit of fear without it causing us to rush towards worse outcomes, we have to come to terms with our fears and how we feel when we're afraid. So the ability to manage fear is a central skill, and it's one that we really don't train. We do train emergency procedures, we train those by rote, but we don't train single pilot or crew fear management. I put myself into the instructor's shoes at a large Part 141 flight school. Now I'm confronted with something that I'm afraid of. Can I see that creating a false sense of urgency or emergency in myself? Yeah, I can see that. In fact, I can see that especially likely when I was early in my flying career. And fear causes us to retreat into the habits that feel safer. If the instructor didn't regularly practice energy dissipating turns, etc., he wouldn't think to try them when the chips were down, when he was under stress. And he might not have been wrong about this either. Real-world emergencies cause us to sink to the level of our training rather than rise to meet the challenge. Knowing in that instant that he was rattled, he may have been right to avoid trying something that he never practices. And this takes us to the value of training and proficiency flying. It's not just about executing a maneuver to ACS standards. It's about getting in touch with all of the cues before, during, and after a particular condition so that you can apply your knowledge in the real world when the chips are actually down, like when you're high and fast and struggling to get energy off the airplane. And that means taking yourself or taking your students into some uncomfortable spots so they get a chance to experience those cues. They should get a chance to feel their perceptions tighten up as their task loading increases, and they should also get some practice loosening up and having their perceptions expand back out as they get their heads back into the game. Having the student become familiar with themselves, their perceptions, and their decision-making in a particular condition is just as important as flying that maneuver to ACS standards. But taking yourself and taking your students into these situations requires some critical judgment. You don't want to zap yourself as you're training, not to zap yourself. You also need to know your student. A demonstration of energy management techniques may inform one student, while another student would see the same demonstration and use that knowledge to place himself in a more precarious situation. You have to know who you're training. These few crashes we looked at all share a similar undesired aircraft state. Too much energy that the pilot could not dissipate. Superficially, this would seem like it's about how to get the airplane lower and slower. But the real issue is information, perceptions, and processing in the pilot's minds. Respecting and understanding how the myriad factors overcame these pilots requires us to respect and understand these pilots themselves. And when we do that, I hope we can learn from their experiences. Thanks for your time. Please comment with your thoughts. I love to hear from you guys, even if you're mad at me. Take care.